Hello friends, this is a presentation for specifically for the GCIT cohort for the week of the last week of April, first week of May, and this is the flipped lesson which I'd like for you guys to use to review, to go over the sound chapter, and I've decided that as per your request, it would be better to use the algebra-based portion for instruction. We'll go through and solve many of the algebra-based examples, and then eventually move into the AP stuff. You'll see that these are so similar. The chapters from the algebra-based and the AP are so similar that it's not going to make much difference. Sound, which is the topic of conversation here, is just a form of energy. When we do work on, let's say, a piano string, it's going to oscillate. So that work that we do in plucking it or hitting a key, it will do work on a string and it will start to vibrate, which is another form of mechanical energy, sound. And it will cause periodic disturbances or repeating disturbances in the air, which travel from the piano through the air to your ear, does work on your eardrum, and eventually gets converted into an electrical impulse in our brain, and we perceive that as sound. So let's do this. See if I can advance the next slide. Sorry about that. Sound is a wave that requires a medium. A medium is simply a material. So sound does require matter to travel, but it cannot travel through a vacuum, so there's no sound in space. Sound will travel in different materials with different speeds. Sound will travel slow in gases and faster in liquids and fastest yet in solids. There is a temperature dependency on the speed of sound in air, and air is a gas. But that's not important in this topic of study. Just realize the speed of sound depends on the medium. So as we go in this direction, we're going from gases, and now we're going into liquids, water, and then into solids. If you go in this direction, velocity is increasing. So if we consider velocity of gases versus velocity of liquids versus velocity of solids, this is greater than that, and so on. This is one of your first test questions. You'll have to be able to recognize the relative speeds of sound in different types of materials. Let's move on. Sound has characteristics, and we can explain these in terms of, I call them properties, or I call this the anatomy and physiology of a wave. The loudness of a wave is its intensity, and that's the amplitude. So I'm going to draw a soft sound wave. We'll have a small amplitude. I use a waveform just to represent that. So if we say that's soft, if I wanted to draw a loud waveform, I draw a wave with large amplitude. So remember, the amplitude of the wave is simply the height from that equilibrium. So that's a small amplitude, and this is a large amplitude. The pitch is its frequency, so I'll draw waves of different frequencies. This is a high frequency, and this is a low frequency. Trying to draw a sine wave. We can hear from 20 vibrations per second to about 20,000 vibrations per second, and that decreases with age. Usually when you hit about the, unfortunately about the 40-year mark, this range of your upper limits of hearing will start to decrease. You can, if you're interested in testing your hearing, you can go to YouTube and type in hearing test. Anything that is above 20,000 hertz, that's above what we can hear, is referred to as ultrasound. So we can use ultrasound for diagnostic purposes. It goes beyond, so we can use this sound to create images. But anyhow, that's above what we can hear. Some organisms can hear or perceive sound at higher frequencies than we can, let's say dogs or bats. And then a sound that is produced or has a frequency below 20 hertz is infrasonic, and there are different organisms that do this. The elephants communicate with each other using infrasonic sound, and turkey do also. The turkey that we see in our backyard, they use infrasonic noises to communicate, to attract each other, and that's called drumming. Sound will travel from a source and then come back, and we can see in this illustration reflection. It's interesting, just like other waves, all of the waves obey certain wave properties. All types of waves can reflect, so we're observing reflection in this slide. The intensity of sound can also be described on the decibel scale, which is logarithmic, and this is not essential to an understanding for what you need to know on this test, so we're going to kind of just breeze through it. But I will say that the intensity of a sound wave is the power per unit area. So if I'm standing here, let's draw me or you, whichever you prefer, and I speak, and there's some sound coming out, that sound will propagate out in spherical waveforms. And as it travels greater distances away, let's say over here, that waveform will spread out over a greater area. So this is a small area. It will be intense at that location. So if I'm standing at that location, it will be loud. Out here we have a large area. It's spread out over a larger area. Therefore, it won't be as intense. If we increase the area, we decrease the intensity. And remember that area of that bubble, if you will, that sound that's being produced is 4 pi r squared. So as r goes up, that distance you are away from that source, r, the area of that bubble will go up and the intensity goes down. Oh, there we go there. The intensity is inversely proportional to the square of the distance. So when you're close to these sound sources, they're very loud. And so enclosed areas are dangerous where there's loud music, because not only are you close to it, so you're getting a very intense, but you're dealing with the reflections of the sound too. Preserve your hearing at any cost. So again, we stated earlier, sound waves will come into your ear. They'll do work on this eardrum, and it will wiggle. In turn, we'll have work done on these tiny structures, the hammer, anvil, and stirrup bones, and it will cause disturbances which go into the cochlea, and at that location there are tiny hair cells which will convert this mechanical sound into electrical energy, which goes into your brain. Other interesting structures within the ear are these things called the semicircular, I think they're called canals, and it's interesting. One of these is located or oriented within the y-axis. Another one is within the x-axis, and then the z. So this allows us to orient ourselves spatially, and often diseases associated with the inner ear, these semicircular canals, will lead to disorientation or vertigo. Meniere's disease is a common disease which leads to tinnitus, which is a constant ear ringing. It can be a disorder with these semicircular canals, and people who have Meniere's disease typically or quite often will become disoriented as a result of that. It's very uncomfortable. So let's move on. A little anatomy lesson. You can read more about that online if you prefer. So our ear and its response to loudness, again, we have these structures. As we stated before in the slide, sometimes it's better to see where they're located before you read about them. You can read this on your own. And our ears' sensitivity, what we can hear, varies with frequency. So our ears are more sensitive to lower frequencies. So if we look here, at this location, we're looking at about 20 hertz, and then up here at this location, We're up there at that upper limit, 20,000 hertz of frequency, and how well we hear depends on which frequency is being played. It seems, according to this slide, this is going to be a sweet spot as to what we can hear. Take some time, go onto YouTube, do this with your students, play the audible spectrum, and there are plenty of videos on YouTube that will play sound that goes from 20 hertz to 20,000 hertz, and it will state which frequencies are being played throughout the video. And you'll note that these middle frequencies, the ones that I just marked there, will be the loudest. So we have a hard time hearing very low frequencies. We have a hard time hearing high frequencies. In the middle, there's a bigger response. You'll see that when you get up here into these higher frequencies, you actually have to turn up the volume for the kids to hear them. And probably you will not hear these high frequencies where they will. So it's a lot of fun. We play that Survivor or Last Man Standing. Who can hear the highest frequency? Good stuff. There are different sources of sound. We can vibrate strings, like in a guitar, or membranes and drums to produce sound, or we can vibrate air columns, like in a trumpet or a trombone or a clarinet, to produce sounds. And in this chapter, I often have them build various types of musical instruments. I make a one-string guitar. I'll share this with you if you prefer. And we make straw kazoos, and we can demonstrate some basic principles of sound. In vibrating strings, we know, and if you have any experience with guitars, if you decrease the length of the string, you will increase the pitch and or frequency of your string. Now I'm going to state this, and you may be familiar with this, but we'll cover it again. The wave equation, the speed of a wave, is dependent on its wavelength and frequency. And we'll just say the speed of the wave in this guitar is going to be a constant. So that will always stay the same. It will never change. So we know that a constant will be equal to the wavelength. Let's just call that the length times the frequency, the pitch. So when the length goes up for your guitar string, to keep that speed constant, the pitch will go down. Long strings play low frequencies, short strings play high frequencies. And why does this velocity stay constant in your guitar? Remember from the previous chapter, the speed of a wave in a coil or a string depends on the tension and the line density. If we don't adjust the tension, if we leave that a constant, the velocity stays the same. So once you tune your strings, you don't play with the tension anymore. And this string itself, its line density doesn't change. So this velocity, which is the square root of tension divided by the line density, remains constant. We'll do some of these experiments that I'm talking about together with straws. In a piano, we use strings of various lengths to produce different musical notes. Also strings of various materials and or line densities. And we know that longer strings and thicker strings will produce different musical notes. In wind instruments, we change the nature of the vibrating reeds to produce different waves. I'm just going to try and draw some waves in these air columns. Can you predict which musical instrument would play the highest musical note? A small saxophone, a medium-sized saxophone, or a large? I think this is an alto saxophone. I think this might be a tenor, and this might be a bari-sax, a baritone. I believe this one will play a high pitch, this one will play a moderate pitch, and this one will play a low pitch. More on that soon. Now, the notes that are being produced in these air columns, not vibrating strings for saxophones, are standing waves. And we can produce standing waves in tubes. I'm going to stop this video and we'll start recording another video, and we'll talk about how standing waves are produced in air columns. More on that in a second.